Hello and welcome you all. This is Professor Barapate, a book author of 25 plus engineering books. This video will give you an overview of digital signal processing, that is DSP. So without wasting the time, let us dive into the topic. In the today's video, we'll be discussing the concepts related to sampling theorem, Z transform, then DFT and FFT. Next is IR filters, and last topic is FIR filters. Dear students, we are talking about DSP. DSP stands for digital signal processing. Processing of signal means making changes in the signal using certain techniques. In all DSP systems, analog input signal is denoted by X of t. As said, this is an analog signal, so it is denoted by X of t. A device is used to convert this analog signal into a discrete signal. That device is a sampler circuit, and corresponding discrete signal is denoted by X of n. So sampler converts continuous time signal or analog signal into a discrete signal, which is denoted by X of n. Now, very important concept related to this is the statement of sampling theorem. What this sampling theorem indicates? This sampler takes samples of input signal. Now there is a particular frequency with which this sample works. This frequency is denoted by Fs, which is called as the sampling frequency. Now first we will discuss the statement of sampling theorem. A continuous time signal, which is abbreviated as CT, can be completely represented in the sampled form, that means in the discrete form, and it can be recovered from its sample form. Means what? If this is the continuous time signal, using sampler I will convert it into sampled form, that is discrete form, and whenever required, if I will join all these samples, I should get original input signal or analog signal as it is. So what we have written, and it can be recovered back from the sampled form if the sampling frequency is greater than or equals to 2W. What this notation W indicates? W is the maximum frequency contained in the signal. Let us talk about one practical example. If I am talking about a speech signal, then in case of speech signal, the frequency range is 20 Hz to 20 kilohertz. In this case, the maximum frequency is 20 kilohertz. So maximum frequency is denoted by W. That means W is equals to 20 kilohertz. So if we don't want any errors, then the sampling frequency Fs should be greater than or equals to 2W. That means it should be greater than or equals to 40 kilohertz. If we won't follow this sampling frequency, then there will be error, which is called as an aliasing effect. We'll discuss this concept in detail. What we have learned, the sampling frequency Fs must be greater than or equals to 2W. This is according to the statement of sampling theorem. Now let us discuss few cases. I am considering a spectrum. Now what is this spectrum? Spectrum is a graph drawn in frequency domain with respect to frequency. So let us assume that after sampling we are getting a discrete signal, and for each discrete signal I will take the Fourier transformation. After calculating Fourier transformation, let us say that for every pulse I am going to get triangles. Why triangles? Why not any other shaped diagram? It is not fixed. I mean, it depends on which type of signal you are using. So as an example, I am considering a triangle. So make it simple. For each pulse of discrete signal, I am getting one triangle. Question arises, why I need to convert the signal into frequency domain or into Fourier transformation? Very simple reason. In case of Fourier only, you are going to get the knowledge of width of a signal. In case of discrete signal, the diagram is like this. On x-axis I have to write n, on y-axis it is x of n, and we are getting the pulses like this. These are the discrete pulses where I'm not getting the idea of width of signal. To get an idea of width of signal, I have converted this signal into the frequency domain. So each pulse, let us say, represent one triangle. If I'm keeping Fs is the sampling frequency. If I'm keeping Fs is exactly equals to 2W, this condition is called as Nyquist rate of sampling. This is very important concept. Do remember it. If sampling frequency is exactly equals to 2W, where W is the maximum frequency contained in the signal, then it is called as Nyquist rate of sampling. And reciprocal of this, that is 1 by 2W, is called as Nyquist interval. Now come back to this diagram. If I am using Nyquist rate of sampling, that is Fs is equals to 2W, then I am getting all spectra which are well separated. I mean to say, there is no mixing of spectrum. Okay, these two spectrum, I mean all the spectrum are one after other, there is no mixing. So this is quite allowed. What is our objective? Our aim is there should not be overlapping of spectrum. Consider another case. If I am keeping Fs greater than 2W, keep in mind, the condition of sampling theorem is Fs should be greater than or equals to 2W. First case we discussed, that is Fs is equals to 2W, where there is no overlapping of sample, but the spectrum are continuous one after the other. In the second case, if Fs is greater than 2W, the spectrum are well separated. There is a gap between consecutive spectra. This gap is called as guard bands because it provides certain type of guard bands between the two spectrum. Third condition, if suppose Fs is less than 2W, that means I am not following this criteria of sampling theorem, then as shown in this diagram, there will be overlapping of samples. This overlapping of spectrum is called as an aliasing. This is a type of error, and this is most important concept. Whenever you are getting overlapping of spectrum, it is called as aliasing effect. When you will get it? If Fs is less than 2W. As I said, this is unwanted phenomena. Now, how to define the term aliasing technically? It is defined like this: if the higher frequency components take identity of lower frequency component because of this mixing of spectrum, then it is called as aliasing effect or aliasing error. Now, next part is, as I said, this is unwanted phenomena. So, to avoid the aliasing effect, two conditions you need to follow. Either keep Fs, that is sampling frequency, always greater than 2W, or use anti-aliasing filter before the sampler. What this concept is? Sampler is a block which converts analog signal into discrete signal. So before applying analog signal, here I am supposed to apply analog signal x of t and output is discrete signal x of n. Before applying this x of t to the sampler, use one filter. This is basically low pass filter, LPF. This filter will avoid all the frequencies which are greater than W to pass through the sampler. That means this filter is used to avoid the sampling effect. So it is called as anti-aliasing filter. Next part is the Z transform. This is also called as a Z domain. We usually work with respect to time period. It is called as a time domain. Likewise, there are different domains. One of the domains is Z transformation, which is widely used in DSP. Now, the notation for Z transform is, if we have a discrete signal x of n, its Z transform is capital X of Z. Whenever domain is changed, capital notations are used. Why bidirectional arrow? Because you can well calculate inverse Z from this. So bidirectional arrow is used. Now these two are mathematical equations which are used to define the Z transformation. In first equation, limits are minus infinity to plus infinity, so it is called as a double-sided Z transformation because limits are negative as well as positive. In second equation, we have used limits from 0 to infinity, which is called as single-sided Z transformation. Now, very important concept, What's the use of Z transformation? Do remember few important advantages of Z transformation because of which it is widely used in DSP. First is it is easy to decide the stability of a system. Next, calculation of difference equation becomes simple. And next, very important advantage is all digital filters can be designed easily using Z transformation. There is one more term related to Z transformation that is called as ROC. It is called as region of convergence. Do remember its definition? It is the set of values of Z for which calculated Z transform will produce some finite answer. Now one more term related to Z transformation you should know, that is a Z plane. What is this Z plane? Z plane is basically a diagram in Z domain, and on X axis we are supposed to plot real part of Z, and on Y axis we are supposed to plot imaginary part of Z. So diagram with respect to real part and imaginary part of Z is called as Z plane. Next important concept related to Z transformation is pole zero plot. I have drawn the diagram of system. Recall the notations. X of n indicates input, H of n is called as impulse response, and Y of n is the output. Output is given as X of n asterisk H of n. This notation asterisk is called as convolution. The notation asterisk is called as convolution. Now where is the question of Z transformation in this case? See, if you want to perform this calculation of convolution in normal domains, then lot of mathematical tools are required. To avoid this, if I will take Z transform of Y of n, it is denoted by capital Y of Z. Z transform of X of n is denoted by X of Z. Z transformation of H of n is capital H of Z. And the beauty of Z transform is this convolution. What I said, for convolution many mathematical calculations are required. If you use Z transformation, convolution simply becomes multiplication. So in Z transformation you are getting the equation of output of convolution as Y of Z is X of Z into H of Z. So from this equation I can write H of Z is equals to Y of Z upon X of Z. Very simple. This I got from the equation of Y of Z. This equation of H of Z is called as transfer function of the system. Transfer function of the system. You will be having some mathematical equation. If you take roots of numerator term, then roots of numerator term are called as zeros, and roots of denominator term are called as poles. If you plot the zeros and poles in Z domain, it is called as the plot of zero and poles with respect to Z domain. Another important concept related to Z transformation is the condition of stability. What I said, one of the most important reason of using Z transformation in DSP is you can easily check the stability. How to do it? In all Z transformation numericals, we are supposed to draw one circle like this. If I have a graph in Z domain, after calculation of Z, you need to draw a circle to show ROC. There are two possible cases. ROC can be region outside the circle, or ROC can be region inside the circle. Let us say radius of this circle is R. Now consider this diagram. I have drawn this circle whose radius is R. There are two terms. One is causality and second is stability. If mod Z means magnitude of Z is greater than value of R. R is what? R is the radius of circle which is used to represent ROC. If mod Z is greater than R, system is said to be causal. And what about stability? If R is less than 1, then the system will be stable. Now, refer this diagram. I have drawn a circle of radius R to represent ROC. For causality, the ROC, which is shown by these shaded lines, must be outside this circle. So I haven't shown any shading inside this circle of radius R. And for stability, R should be less than 1. whenever you will draw a circle of radius 1, it is called as unit circle. So in this case, this circle is called as unit circle because its radius is 1. If I will mark in this diagram, this radius is 1. So condition is r less than 1. That means this unit circle must be greater than r, or in another language, unit circle must be in the ROC region. So if I want to write the combined condition of causality as well as stability, it is mod z greater than r, where I have used this condition, first condition, and r less than 1, I use the second condition. So combined condition for a system to be causal and stable in z domain is mod z greater than r and r should be less than 1. Next important topic in DSP is DFT and FFT. DFT stands for discrete Fourier transform and FFT stands for fast Fourier transform. We should know the notation of DFT. If x of n is the signal, its DFT is capital X of k. This is the mathematical formula to calculate the DFT. Now, one important term in DFT is the twiddle factor. This is the mathematical term which is denoted by w to the base n, and its value is e raised to minus j2 pi by n. So, in the defining equation, instead of e raised to minus j2 pi by n, if I will use value of wn, then this will be the mathematical equation to calculate the DFT. So students should know both these mathematical equations for the calculation of DFT. Now another important concept related to the calculation of DFT is circular convolution. Do remember, normally in discrete domain we perform linear convolution, whereas in DFT we are supposed to perform circular convolution. You should know the mathematical formula to calculate the circular convolution. What this concept is, if suppose I have the sequence x of n and values are 1, 2, 3, 4. We know how to plot the graph linearly, but if you want to write the sequence circularly, it is denoted by x of double bracket n. How to do it? There are 4 samples, so I will draw a circle. I will divide the circle into 4 parts. As a convention, this point is taken as a starting point, and convention is I need to write the values in anti-clockwise direction. So I need to mark the values like this: 1, 2, 3, 4. It is called as circular plotting of sequence x of n. Now there are few terms related to this. One is delay of this sequence. Do remember the basic concepts. Delay is just go on rotating the samples in anti-clockwise direction. For example, if I want to delay these samples by 1 position, then this point number 1, where I have marked it as a starting point, this will be shifted in anti-clockwise direction like this. So now at this position I need to write 1, at this position I need to write the second value, and so on. Very simple. Simply delay means rotate the circle in anti-clockwise direction. And one more term related to this is advanced. Advancing means rotate the samples in clockwise direction. So only 2 rules you need to remember. First, if you want to plot the samples in terms of circular fashion, then draw the circle and mark the samples in anti-clockwise direction. Delay means rotate the samples in anti-clockwise direction. Advance means rotate the samples in clockwise direction. So this is the part related to circular convolution. Now from the exam point of view, important part related to circular convolution is, as I said, in normal domain we have linear convolution, whereas in case of DFT we are supposed to perform circular convolution. Now do remember some notations. Earlier we had drawn this diagram. Here we have written input x of n, output y of n, and this is the block diagram of system whose response, which is called as impulse response, is denoted by h of n. So y of n is given as x of n asterisk means linear convolution, h of n. This is the linear convolution. The number of samples contained in X of n is denoted by L. Number of samples contained in H of n is the impulse response, is denoted by M. And number of samples contained in the output of linear convolution is denoted by N. From the exam point of view, you should know the formula of N. It is L plus M minus 1. This is the formula which gives the number of samples in the output signal sequence which you are getting after performing the linear convolution. In case of circular convolution, see, this is the output of linear convolution, whereas if you perform circular convolution, you won't get this output same as the linear convolution. Now the question can be easily asked in any exam like this: how can you obtain the result of both linear and circular convolution same? Very simple. Do remember the basic things. In case of X of n, what I said, number of samples contained in X of n is denoted by L. In H of n, it is denoted by M, and this is the formula to calculate n. If you want to obtain same answer of both convolution, first calculate value of n. How to do it? Suppose number of samples in X of n is 4, number of samples in H of n is also 4. Then according to this formula, I will get the value of n, that is 4 plus 4 minus 1, which is 7. So if you want to obtain the result of circular convolution same as that of linear convolution, what do you need to do? Initially there are 4 samples in X of n. Okay? Let us assume some sequence of X of n. Suppose given sequence is 1, 2, 3, 4. This is initially given sequence. What I will be doing? I will be calculating value of n using this formula. But there are 4 samples. Calculated value of n is 7. I need to make length of X of n 7. So since I have only 4 samples, I will be adding 3 zeros. Addition of zeros in any sequence to adjust the length, this effect is called as zero padding. Again, do remember this word. This is important word related to DFT. If you are adding zeros anywhere to adjust length of sequence, it is called as zero padding. So what I am supposed to do? Adjust the length of X of n, which is equals to n, that is 7. Similarly, whatever sequence you might be having for H of n, make its length equals to 7. Then perform circular convolution. In such cases, you will get answer of circular convolution same as the linear convolution. Do remember, it is very important concept. Now, the remaining part is the linear filtering of long data sequences. For that, overlap save and overlap add methods are used. Dear students, I have created a separate video on overlap save and overlap add method. I will provide the link in description box. Please watch that video. So I'm not going to cover that part in this topic. Next is the concept of FFT, fast Fourier transformation. Obvious question is, as the name indicates, it is fast Fourier transformation. So if this question is asked, let us say in the Viva, students say like this: it is faster than DFT. No. It's not faster than DFT. Actually, the required number of calculations in case of FFT. In FFT, there are 2 algorithms. One is called as DIT. D stands for decimation. Decimation means splitting or breaking the sequences. Decimation in time. Second algorithm is DIF, which is decimation in frequency. So these are the 2 algorithms. What is the concept of FFT? Suppose I have one sequence X of n in which there are 8 samples starting from X of 0, X of 1 up to X of 7, 0 to 7. That means there are total 8 samples. In case of DFT, we are supposed to calculate Fourier transform, that is DFT, of each sample separately. So I need to do the calculation 8 times. In FFT, there are different stages. What I am supposed to do? First, split this given sequence into 2 parts. In the first part, take only even samples. In the second part, take only odd samples. This is called as first stage of decimation. Decimation means breaking or forming blocks. So after performing first stage, let us say I have getting sequence F1 of n and second sequence F2 of m. These are just notations, no technical meaning. So both F1 and F2 will contain 4 samples each. That means if I want to perform the calculation of Fourier, I need to calculate 4-point DFT, as well as for second I need to calculate 4-point DFT. But this is not the end of process. Again split or divide this sequence into two parts. So finally I will be getting 4 sequences which will contain 2 samples each. So final stage is do the calculation of 2-point DFT. So naturally, if I will be doing calculation of 2-point DFT separately and parallelly, then time period will be reduced. Instead of calculating Fourier of one sample, then second sample up to the 7th sample, that is you need to calculate DFT 8 times. Instead of that, in this process you will be calculating DFT, that is Fourier transform of only 2-point DFT. And do remember this word, the hardware structure which is used to calculate 2-point DFT is called as butterfly diagram. Now what these algorithms indicate? So what I said, there are 2 algorithms, one is DIT and another is DIF. This algorithm indicates that initially I am supposed to calculate 8-point DFT, but what I am doing, I am doing the calculation of 2-point DFTs. So the algorithms indicates that first combine these 2-point DFTs, form 2 sequences which will be having 4 points. Again combine it and generate the original sequence after calculation of DFT. From the exam point of view, how to answer this question, why FFT is faster? You need to remember these mathematical formulae. If you are using direct DFT, that means you are not using FFT, then complex multiplication. Why this word complex is written? The values can be complex, like 1 plus 2j. It is called as a complex number. So complex multiplications are n square, complex additions are n square minus n. N is the number of points whose DFT you are calculating. For example, if x of n is having 8 samples, it is called as 8-point DFT. And in this case, value of n will be 8. But if you are using FFT, following this structure, whatever I explained right now, then these are the equations to calculate complex multiplications and complex addition. If you put the value of 8 and if you do the calculation on the calculator, you will come to know that the required number of multiplication and addition are drastically reduced in FFT compared to DFT. So FFT is faster than DFT. The next topic is IIR filters. IIR stands for infinite impulse response. As we discussed earlier, impulse response is denoted by h of n. Infinite impulse response means there are ideally infinite number of samples contained in h of n. One of the important characteristics of IIR filter is that they are recursive filter. Do remember this word, recursive filter. That means there is a feedback signal. What's a feedback? Feedback is the signal which is fed back from output to the input. Now, from the exam point of view, you should know what are the different techniques used to design IIR filters. So, 2 prime important techniques are impulse invariance method and BLT. BLT is called as bilinear transformation. So BLT is bilinear transformation. Now, do remember one more basic thing. All analog filters are designed using Laplace transformation. The variable s is used in Laplace transformation, which is expressed as s is equals to sigma plus j omega. This notation is sigma, which represents attenuation in the signal, whereas this notation omega is frequency of analog signal. Then another thing is all digital filters are designed using Z transformation, and variable Z is expressed as R e raised to j omega. R represents magnitude, whereas omega is frequency of digital signal. So omega is angular frequency, which also represents frequency of digital signal. Now, most important concept related to IIR filter is the Butterworth approximation technique. What is this approximation technique? If we consider an example of low pass filter, As the name indicates, it is LPF, low pass filter. So it passes lower frequencies. In ideal cases, the response of filter should be like this. So this particular thing from 0 to say particular value FC is called as cutoff frequency. This is called as a pass band. That means from 0 to FC all frequencies will be passed. But in practical cases, you won't be getting this ideal response. Rather, you are getting this type of response. That means there are variations, ripples present in the response. To avoid this or to obtain the practical response much closer to ideal response, one of the well-known approximation technique is used, which is called as Butterworth approximation. Now, this graph shows the characteristics of Butterworth approximation filter. Mod of h of omega square is called as magnitude squared response. On x-axis we are plotting omega. Omega is the analog frequency. So Butterworth approximation is applicable for analog frequency. Accordingly, we have to make changes in the specification and then apply either impulse invariance or BLT, bilinear transformation, to obtain the desired digital filter. Now, what are the notations used in Butterworth approximation? Ideal response is at 1. This term epsilon, this term represents attenuation in the pass band. Then this term delta represents attenuation in the stop band. Omega p is pass band edge frequency. That means from 0 to omega p there will be a pass band. Omega c is called as cutoff frequency. Omega c is cutoff frequency, whereas omega s is called as stop band edge frequency. That means at this point stop band starts. The last topic is FIR filters. FIR stands for finite impulse response. As the name indicates, impulse response, we know that it is h of n. So as the name indicates, in case of h of n, there are finite number of samples. That is, length of h of n is finite. And do remember one important word related to FIR filter, that FIR filters are non-recursive, means there is no feedback. Two important characteristics of FIR filter one should know, that is, FIR filters are linear phase filters. FIR filters are linear phase filters. That means phase response of FIR filter is always linear. And second important characteristic is FIR filters are inherently stable. FIR filters are inherently stable. That means by default FIR filters are stable. So these are important characteristics of FIR filter. Two well-known methods are available for designing digital filters, digital FIR filters. One is windowing method and second is frequency sampling method. What is the concept of window? Consider HD of n. HD of n is desired impulse response, which is having, say, infinity number of samples. We are talking about FIR filter, so infinite number of samples are not allowed. How to take out finite number of samples from this sequence? So for this, I have written one notation, WRN. W stands for window, R means a rectangular window. So if I want to draw the ideal characteristic, then a rectangular window is like this. From 0 to m minus 1, its amplitude is 1. This is the rectangular window. So I am considering rectangular window. This diagram I have drawn in discrete domain, so it is in the form of pulses. If you multiply HD of n, do remember HD of n is infinity duration sequence. If you multiply it with WR of n, only limited number of samples of HD of n, that is the samples from 0 to m minus 1 will be taken out. So H of n is HD of n into WR of n. WR of n is called as window function for rectangular window. What is the major problem of rectangular window? It is called as Gibbs phenomena. Do remember this word, it is very important phenomena. See, in case of rectangular window, At 0 amplitude is 1. This amplitude 1 remains as it is till m minus 1, where m is called as the length of FIR filter. At m minus 1, suddenly amplitude becomes 0, which was initially 1, suddenly it becomes 0. Due to this sudden change, there are variations in the passband, that is from 0 to m minus 1 as well as after m minus 1. These passbands are called, these ripples represents variations in passband and stopband. So this is the major problem of rectangular window. Why it happens? Because there is a sudden change in amplitude from 1 to 0 at m minus 1. This concept is called as a Gibbs phenomena, which is unwanted phenomena. How to avoid it? To avoid it, other types of windows are used. For example, Hamming window, Hanning window. The wave shape is like this. That means similar kind of response you will be getting, but there is not a sudden change. It is not having the shape of rectangular. So it is like this. There is a smooth variation. So these are the different window functions which are available for designing of FIR filters. Dear students, this is just an overview of the subject digital signal processing. I will upload some new videos related to designing and calculations of digital signal processing. Till then, keep watching educational videos and of course keep studying. Thank you. Thanks a lot.